Hi, everyone. My name's Neha. Was just said, I'm a data scientist at Stream, where we build chat and newsfeed components that our customers can use to implement these features with all the headaches and overhead that come with implementing chat and newsfeeds in-house. I work on the machine learning team, where we work primarily on chat moderation. Specifically, we in the past worked on detecting toxic messages, explicit messages, and currently we're very focused on commercial spam moderation, which we'll talk about at length today. Also, we work on personalized feeds as well. Before I get started, I want to give a quick shout out to my lovely coworker, Kiara, who's hanging out in the chat and ready to answer any of your questions throughout the talk. I'll also be in the Stream booth directly after the talk for a quick Q&A session. So yeah, come join me if you have any unanswered questions at the end of this talk. But yeah, let's get started. Let's talk about machine-generated text detection. So today we'll talk about how machine-generated text detection can be used in finding and stopping commercial spam and how it can be useful in that task. We'll learn about different types of machine-generated text. We'll run through simple techniques that we've tried at Stream that we're still evaluating, and we'll also discuss future work. So what is commercial spam? So this is repetitive content which aims to promote, advertise, or direct recipients to take a specific action. So this can take the form of asking users to visit some sort of URL, repeated mentions of products, companies, people, that sort of thing. Commercial spam typically happens without regard for the context and flow of the conversation, the chat conversation, and it's primarily high volume, indicated by high volume. And it's usually similar content or identical content. You'll frequently see spammers switch out words and characters, but they tend to be fairly similar. So in our discovery, we found that a number of our customers have issues with commercial spam. The drawbacks include a deteriorated quality of chat, which keeps users from returning to their app. You know, when you have high volumes of spam messages happening, it really ruins the flow of the conversation and makes it quite a frustrating user experience. You also see mentions of competitors, which can draw users off our customers' apps and result in lost revenue. Also, it can be very difficult to implement your own in-house solution. Two very common solutions we've seen our customers try to work with are regexes. So people are looking for phrases like buy, click. They'll look for emails, phone numbers, mentions of WhatsApp, Venmo, Cash App, that sort of thing. Or our customers will look for users that have seemingly supernatural volumes of chat messages that normal users should not be able to achieve. Both of these solutions work quite nicely, but they're also very easy for spammers to circumvent. Like I mentioned before, you can get past regex filters by just switching out characters or adding extra words. Users with high volume messages that are getting blocked can create new accounts. So yeah, our customers require a complex spam moderation tool. So why do we care about machine-generated text in commercial spam? So large language models are getting better and better at producing text that is seemingly written by humans or indistinguishable from text written by humans. So bad actors can use text generation capabilities to quickly and easily generate spam. Spammers can also utilize machine-generated text to bypass simple spam filters. So if we can catch spammers when they start using machine-generated text, we can stop them before they reach really high volumes of messages. Or if they are starting to use machine-generated text to bypass spam filters, we can catch them before their circumvention techniques start to get more and more sophisticated. So detection of machine-generated text could significantly boost the ability of our classifiers to catch commercial spam. So what are the differences between human and machine-generated text? So these are observations I've personally noticed, and also observations I've seen in literature. So modern text generation models sample more common words to prevent nonsensical output. So what this means is text generation models usually look at prior words to generate the next word, and they usually pick the highest probability or one of the highest probability words. The sampling technique that quite a few models use, like something like top K, for example, really truncates the number of words you can use to more common and more high probability words to prevent nonsensical output. This has the nice byproduct that it has lower diversity in word choice than human-generated text. So we can kind of exploit that to our advantage with those sampling techniques, at least. So kind of related to that, entropy seems to be higher for modern text generation models compared to human-generated text. Interestingly, the opposite is true kind of for older text generation models, which might have more nonsensical output, more words that you might not expect to see in regular human language. Just a quick explanation. If you're not so familiar with the concept of entropy, it's basically a measure of how expected, for example, if we're talking about text, how expected the words in the message are. So messages with a lot of uncommon or low probability words have high entropy. Messages with more common words will have low entropy. We've also looked at using techniques like percentage of non-alphabetical characters. Shout out to Kiara for trying that with commercial spam and inspiring me. And capitals, which can be significantly different between the two types of text. Transition probabilities can also vary greatly between human and machine-generated text. So that basically means what is the probability that a word is followed by another word. So uncommon transitions with high probabilities could be quite common in older messages from older text generation models. For newer, it could be that very common transitions have abnormally high probabilities. So yeah, let's talk about these techniques a bit more. Oh, sorry. Before that, I'll show you some examples of machine-generated text. So here's some simple examples. So when I talk about kind of older techniques of generating machine-generated text, this is very similar to some examples I've seen in our customer data. So kind of at a high level, if you're kind of skimming through, it seems to have some sort of syntax. If you just read the first few words, it might seem like a real message. Once you start reading, obviously there's no meaning in the message. So this is kind of what I refer to when I talk about simple examples of machine-generated text. For complex examples, I've taken this data from a data set of Amazon reviews, both human-generated and generated by a text generation model called GPT-2. We'll talk about this data set a bit more in length later. But this first one, love this product. I bought one for my girlfriend and her sister for a Christmas gift. As I write this review, both have it in their husband's royal homes. So husband's royal homes is definitely like a very uncommon word choice. Also, there's a bit of a logical fallacy here. It seems as if the reviewer's girlfriend also has a husband. So it definitely seems nonsensical, or they have a complicated relationship. I don't really know. Edit, I just contacted the company and they assured me they would be very responsive in making sure my issues are further addressed. P-sources, so as you can see here, there's long stretches of text that seems reasonable, and then there's like a few tells you can see, like husband's royal homes, P-sources seems very odd. The next two are fairly convincing, I think. I read several of these women's killers club books and enjoyed them very much. Great escapism for a day of reading. So women's killers club books seems like an odd word choice, but it could refer to something. So it is a bit more convincing. So far, I like it a lot. Only time will tell whether it lasts. I like the 2-position clicking and have not put a lot of hours on it. This is referring to a review on a mouse. Have not put a lot of hours on it is definitely an odd word choice instead of saying something like I haven't been able to use it much. But the last two are fairly convincing. So as you might have picked up in the last slide, longer passages generated by text generation models kind of create tells more so than shorter messages. That first message you could pick up fairly quickly that it's not generated by a human. This can pose a problem because most chat messages tend to be short, especially in comparison to something like Amazon reviews. Luckily, some other members of our team were able to spot that commercial spam messages seem to be greater than 120 characters, but it could still pose a problem, especially for messages that are close to the threshold. Another limitation is that the most effective detectors are created by fine-tuning the text generation model that was used to find text generated by that same model. So what this means is if a spammer is using a model like GPT-3, the models that can detect those messages in the literature are fine-tuned on that same GPT-3 model. Similarly, if someone's using BERT, the best results you're going to see is from fine-tuning a BERT model. So this definitely poses a problem because we don't have an easy way of knowing which model a spammer is using within our own chat data. We can try to characterize this a bit more using pre-trained models, but yeah, we want to find something that works well for all these different models. Another one of my concerns is that detectors could result in false positives for non-native English speakers who might not have the same word choice as more fluent English speakers. This could also be true depending on how we get our chat data, if it's all coming from customers in certain regions. So even if they're fluent, word choice can definitely vary from region to region. So I think this could result in bias and is something we need to be very careful about. Another huge limitation for us is we have a small data set. I'm working with 2, which I'll get into more. One is hand curated, so you can imagine how laborious that process is. It's about 5,000 messages. Our Amazon review data set is about twice that. So after considering some of these limitations, I thought the best place to start was just looking for simple metrics that we can use to weed out some of the more obvious examples of machine-generated text, and also metrics that could work at detecting both simple and complex text generation models. So we mentioned entropy before, average word length, percentage of numbers, percentage of capital letters, percentage of non-alphabetic characters were all different metrics I tried. I also tried just building a simple machine-generated text detector. This is more so for me to understand the differences in the data I have found within our customer data between the machine-generated and the human-generated text. It also will help us find similar messages to kind of expand our small data set. And then another thing I tried was transition probabilities, which I talked about before. So my two data sets I was working with, one represents the simple machine-generated text. So that's our internal chat data. I was able to find messages that are very obviously machine-generated. So this is my smaller data set, 5,000, split between human and machine. I also have a complex machine-generated text data set, and that's the Amazon review data that you saw previously, and that's generated by GPT-2. Obviously, Amazon reviews differ from chat messages, but I think in looking at this review data, we can try to narrow down some techniques that we can use on our own internal data. So the first thing I tried was looking at entropy. So our hypothesis was that simple machine-generated text will have higher entropy than human-generated text, and that the opposite will be true for more complex machine-generated text. So you can see on this figure on the left, this is from our internal chat data. The data in orange is the machine-generated text. You can see some nice separation when you look at entropy per word. I used entropy per word to get some sort of normalization to make sure that the metrics are consistent between message length. But yeah, you can see some nice separation. You can see that we could even do a pretty simple cutoff to get rid of more obvious machine-generated text, and there is some nice separation, which gives me hope that entropy can be a nice feature to use in the future. When you start looking at the Amazon review data, though, it starts to look less promising. The distributions are nearly identical. You can see some small differences, but nothing significant. So my theory is that when you look at something like an Amazon review, the structure and the syntax is a lot more orderly than chat data, which can have, typos, links, images, all sorts of things that don't exist within Amazon reviews. So I'm hoping that when we apply this to our own chat data, we'll see a bit more separation, but I have no proof as of yet. So I also tried percentage of characters that are not in the alphabet. Once again, you can see some really nice separation for our internal chat data. Not so much for the Amazon review data. If you kind of zoom in on the low percentage areas, you can see some separation, nothing super significant, but this could be useful. Same thing with percentage of capital letters. Once again, distributions look different with our internal chat data. Not so much with the Amazon review data. When you kind of zoom in on the tail, obviously these are different regions, but when you zoom in on the tail, you do see some difference, but nothing very significant yet. I'm hoping with our chat data, this could be a useful feature along with percentage of characters not in the alphabet. So another technique I tried was to build a simple classifier for simple machine-generated text. So my goal here wasn't to create something that was production ready necessarily. It was more so to train a simple classifier so I can kind of understand the differences between the human and machine-generated text that I found and repurpose this model to find more training data that's very similar to our machine-generated text. Our simple machine-generated text. So I was able to train a naive Bayes classifier with an F1 score of 99% on test data. That already is a bit of a red flag to me that it might be overfit, but it can still be useful. So when I look at the top predictive words that are generated by this model, for human-generated text, you can see things like HTTPS. So this seems promising because we're looking at secure URLs. Then you can kind of see some common words like views, met, active. They're not crazy common, but once again, I'm working with a limited data set, so I'm curious to see how this evolves as I get more data. For machine-generated text, the top predictive words are things like misses, actuality, authors, LLC. I think that LLC is really interesting. It seems like it's picking up on proper nouns, which is very interesting. The other words, it kind of, once again, seems like it might be picking up on certain messages in the data set, so it could be overfit. And that's kind of what I realized when I applied this to the Amazon review data. The F1 score was barely better than random chance. So this model is definitely overfit, but could be useful for finding similar content. And then the last thing that I've been working on, and work is still in progress, is transition probabilities. So as I've mentioned before, transition probabilities are the probability that one word is followed by another word. So I think this could be really useful, especially like when we looked at some of the simple machine-generated text examples. You could see some very strange combinations of words. And you can kind of see that in the more complex machine-generated text examples as well. But actually my theory there is that because of, especially if you're using sampling techniques like top K, you're actually going to see very common common transitions have higher probability than they do in the human-generated text. So yeah, I kind of started working on that. I just kind of simply looked at the highest probability transitions in our chat data and like between human data and the simple machine-generated text. Excuse me. So a lot of these transitions are fairly common, which I was hoping for. So these results seem to make sense. For our simple machine-generated text, you definitely see the highest probability transitions being quite odd. So yeah, I think this work can be really promising. I think obviously the way, simple machine-generated text and complex machine-generated text differ from human-generated text are going to be quite different, but I think this could be very useful. So yeah, in terms of future work, we're looking at applying simple techniques like entropy per word and the naive Bayes classifier, both to identify machine-generated text and also generate a bigger data set. We also are looking to use pre-trained machine-generated text detectors to search for more complex machine-generated text within our customer data. It's just to understand the problem that our customers are dealing with a bit more. And then I think what could be quite useful is treating machine-generated text detection as an anomaly detection problem, where we have some sort of characteristics that we've identified for our chat data. Because obviously different machine-generated text generated by different models, the behavior varies greatly. So I think anomaly detection could be an interesting way to solve this problem. All right, so just to wrap things up, detecting machine-generated text can help us detect spammers quickly, help detect spammers who are working to circumvent spam filters. Detecting simpler forms of machine-generated text is fairly easy. The complex forms are less straightforward, unfortunately, but I think we still found some interesting results that we can use to find those as well. Simple metrics could be used to filter out messages that are very obviously machine-generated. And then obviously, as text generation models get more sophisticated, our approach will also have to evolve. As I think Rodrigo, who's in the chat too, generally says it's a game of whack-a-mole. So you find some way of catching spammers. They find a way of evading that detection. So yeah, it's definitely an interesting problem. Which leads me to, if you also think this is an interesting problem, and content and chat moderation are very fascinating, Stream is hiring. We're searching for an NLP ML engineering lead who'd be working directly on this problem. We're also looking for a Python Go backend developer. So please reach out if you're interested and have any questions. And yeah, I've kind of linked some sources that I found very useful in this work. Hopefully these slides get shared. And yeah, that's all I have for you guys today. Thanks so much for your time and attention.